Good morning, everybody. This is second lecture of FIBSc Physics Principles and Application. It is paper first year, chapter number 2, laser here. Last time we saw what is the acronym for laser, means what is the long form of laser. Laser means light amplification by stimulated emission of radiation here. Then we saw here what is absorption, what is spontaneous emission, and what is the stimulated emission here. Just we have revised all this here. What is absorption here? It is the revision of that here. Absorption means here the atom are already in the ground state here, so it is your E1 here, and it is your E2 here. It is the atom in the higher energy over here. When we supply some energy from the external source here, the atom goes to the higher energy over here. So here by supplying some energy to the atom which are in the ground state here, the atom goes to the higher energy. It is called the absorption here, and we define that A star gives you A star. It is your A plus H2 gives you A star here. So here this is nothing but the absorption here. Then we saw here what is the spontaneous emission here. Now as we know that here atom is already in the higher energy over here. So here after 10 raised to minus 8 second here, the atom at its core here goes to the ground state energy over here. So here it is nothing but the A star gives you A plus H2 here. The difference is radiated in the form of photon here. It is nothing but spontaneous emission here. And what is the stimulated emission? Stimulated emission here. Then what happens here? We have to supply some energy to the atom which are in the higher energy here, and that atom we have to transfer to the ground state atom here. So the equation for that here A star plus H nu gives you A plus twice H2 here. So we define all these things here in the last lecture here. So it is the revision of that here. So we know that here in the case of laser here, we know what is the acronym for laser here, what is the absorption, what is spontaneous emission, and what is the stimulated emission here. Today we have to see here. Last time also we saw here what is the population inversion here. So we know that here atom here, what is the population inversion here. Normally what happens here, this is the ground state energy level E1 and this is the higher energy level E2 here. The population of the atom in the ground state energy level is N1 here, and the population of the atom in the higher energy level is N2 here. So here N1 and N2 are the population of the atom in the ground state energy level and higher energy level here. And normally what happens here, now here N1 is always greater than N2 here. So this is the normal case here. So here in this case here, the population of the atom in the ground state energy level N1 is always greater than the population of the atom in the high energy level here. So then here, what is the population inversion here? Last time we saw here population inversion here. Population inversion here. Now here population inversion means here a stage is reached here in such a way that here N2 is greater than N1 here. If this stage is reached here, this is called the population inversion here. Means population of the atom in the higher energy level. If it is greater than population of the atom in the lower energy level here, it is called the population inversion here. Now today we are now here it is very impossible thing here. It is very hard thing here. But we require for laser action we require the population inversion here. But we must know here how it is related with the temperature here, how the atom in the higher energy level increases here. So that we have to see today. We have to see the derivation formula here. So it is called the thermal equilibrium here. The article is thermal equilibrium here. So here as we know that here last time I told you that here. So here this is the ground state atom here. It is your N1, it is your N2 here, it is your E1 and it is your E2 here. So these are the ground state energy level, higher energy level here. Number of atom in the ground state energy level N1 and the population of the atom in the higher energy level N2 here. So what is N1 here? N1 is equal to E raised to minus E1 upon K here. So this is the equation for that here. The population of the atom in the ground state equation, ground state level is N1 is equal to E raised to minus E1 upon K here. Where E1 is the ground state energy level, K is the Boltzmann constant here, and T is the temperature here. And what is the population of the atom in the higher energy level N2 is equal to E raised to minus E2 upon Kt here. So here we put it. So here it is your N1 and N2 here. So here N2 upon N1 is equal to. So here what is our equation here? What is N2? E raised to minus E2 upon Kt and divided by E raised to minus E1 upon Kt here. So this is the equation here. So here it is the denominator here goes to the higher energy here. It becomes plus here. So what is our equation? It becomes here E raised to minus E2 plus E1 upon Kt here. So here we can rearrange the terms here. So here it is here E1 minus E2. So E1 minus E2 this is the equation here. We can check the negative sign outside the bracket here. E raised to minus, it is E because here E2 minus E1 upon KT here. Why we take this equation here? So here E1 minus E2 is not possible here. Why it is not possible here? We must look for that here. So here just we have to divide all this thing here. So we know that here in the atomic in the first chapter here we know that here. So here it is your E1 is equal to minus 13.4 upon n square here. So it is the energy level for the 13.6 here. I think it 13.6 electron volt upon n square here. So here what is it is your E1 here? What is E2? E2 is equal to minus 13.6 divided by 2 square, which is equal to minus 13.6 divided by 4. It is equal to, it is near about 3.21 here electron volt here. It is minus 1 here. So it is your E1, and for E1 here it is equal to n by it is minus 13.6 electron volt here. So thus here we got here E1 is equal to minus 13.6 electron volt, and E2 is equal to, it is nearly equal to 3.21 electron volt here, which is written here. So here this is both are negative here, but it is small negative, it is big negative here. So we know that here E2 is greater than E1 here. So remember here E2 is greater than E1 here. So here E1 minus E2 is possible. It is imaginary here. It is not possible here. So here E2 minus E1 is possible here. That's why here we have to make some changes in this equation here. It is E1 minus E2. E1 minus E2 is not possible. Why it is not possible? Because E1 is equal to minus 30.6 electron volt here, and E2 is equal to minus 3.20 electron volt here. So here in this case here E2 is greater than E1. So E2, so here that's why here E1 minus E2 is not possible here. So as E2 is greater than E1 here, E2 minus E1 is possible here. So this is correct here. So that's why here we have to make some changes here. The negative sign that we have to take outside the bracket here. This equation become here. It is E raised to minus. It is E raised to minus into minus C1 upon KT here. So this is nothing but the ratio of the population of that in the higher energy level to the lower energy level here. So we can write this equation here. So here. So we come up to this step here. So it is your N2 upon N1 is equal to E raised minus E2 minus E1 upon KT here. So it is your, this is the equation here. So we know here it is Planck's law. We know E2 minus E1. What is E2 minus E1? E2 minus E1 is equal to H2 here. So E2 minus E1 is equal to H2 here. So it is the equation here. So we can rewrite this equation. It is E raised minus H nu upon KT here. So here this is the equation here, but we don't require this equation, we require this equation here. So suppose it is equation number 1 here. So then we can find out here at normal room temperature here. As already I told you that here at normal room temperature what happens here? The number of atoms in the ground state atom. So here it is your E1, it is your E2 here, it is your N1, and it is your N2 here. So here at normal room temperature we say theoretically that here the number of atoms, all atoms are in the ground state atom here, and the number of atoms in the ground state at normal room temperature it is nearly equal to 0 here. So that we have to prove here. How can we prove that here? Suppose here in this case here T is equal to 27 degrees centigrade here, or it can be written as it is your 300 degree Kelvin here. So what is K Boltzmann constant here? The value of Boltzmann constant K is, it is nothing but the 8.61. It is your 8.61 into 10 raised to minus 5 electron volt per K here. So this is the value of Boltzmann constant here. So we can find out this ratio here. So we can find out the ratio here. So it is your, and so here we record KT here. So first we can find out here what is KT. K into T is equal to 8.61 into 10 raised to minus 5 electron volt per Kelvin into 300 degree Kelvin here. So the answer of that it is nearly equal to 0.025 here. So we have to substitute in this equation here. What is E1? E1 is equal to minus 13.6 electron volt, and E2 is equal to, it is near about the 3.24 electron near about that here. So we know that here E2 minus E1 is nearly equal to 10.21 here. It is 10.21 electron volt here. It is minus, it is here E2 minus E1 here. So it is plus 10.21 electron volt here. So here if we supply that here, substitute into upon N1 is equal to e raised to minus 10.21 divided by 0.025, and this equation becomes here, the value of that become here, it is equal to e raised to minus 408.4 electron volt here, and it is nearly equal to 0. So here N2 upon N1 is equal to 0. So here N2 is equal to 0 here. N2 is equal to N1 into 0. So here N2 is equal to 0. From this derivation here, we prove that here. So here this is ground state energy level. It is your E1 and it is your E2. These are the population of the atom in the ground state, and this is the population atom in the higher energy area. At T is equal to 27 degrees centigrade here. At T is equal to 27 degrees centigrade means here 300 degree Kelvin here. We know that here, we prove that here. Theoretically, we say that here, at normal room temperature, almost all atoms are in the ground state here. Now here we mathematically prove that here. So here N2 is equal to 0. At normal room temperature here, the number of atoms in the higher energy level or population of the atom in the ground state energy level is equal to 0 here. So means that here all atoms are in the ground state here. There is not a single atom in the high energy level here. Now then what we have to do here? We have to increase the temperature here. Now here in this case here, from normal room temperature to we have to increase the temperature to, suppose here at T is equal to 10 raised to 4 degree Kelvin here. So we increase the temperature here. At 10 raised to 4 degree Kelvin here, what happens that we have to see here. So then what is it here KT? So here this K into T become, it is 8.61 into 10 raised to minus 5 electron volt per Kelvin into 10 raised to 4 degree Kelvin here. So then what is our equation here? This become here, it is 10 raised to 4, 10 raised to minus 5, 10 raised to minus 1 here. So it become here 0.861 into 10 raised to not here. It is your per Kelvin gets us, it is your electron volt here. So KT is equal to this here. And we know that into minus 7 is equal to minus 20, it is 10.21 electron volt here. Then at 10 raised to 4 degree Kelvin here, we increase the temperature. It is the tremendous amount of temperature here. We require that here. So what happens that we have to see here? After temperature increase in temperature here, what happens here? This N2 upon N1 become here. It is nothing but E raised to minus 10.21 electron volt divided by, it is 0.861 electron volt here. So near about this becomes here, it is near about E raised to, it is equal to E raised to minus 11.85 or it is equal to 7 into 10 raised to minus 6 here. So we got this, this is the equation here. So here N2 upon N1 is equal to 7 into 10 raised to minus 6, or we can write here N2 upon N1 is equal to 7 upon 10 raised to 6 here. So this is the equation here. So what we got here? We got at 10 raised to 4 degree Kelvin here. At 10 raised to 4 degree Kelvin here, N2 upon N1 is equal to 7 upon 10 raised to 6 here. So here, what is the meaning of that here? So here we increase the temperature from ground state to normal room temperature to 10 raised to 4 degree Kelvin here. Then what happens here? N2 upon N1 becomes 7 upon 10 raised to 6 here. What is the meaning of that here? Out of 10 raised to 6 here, only 6 to 7 atom goes to the higher energy here. Means remember that here. So here, as already I told that here, N1 is so here it is your N1 is greater than N2 here. It is always greater than N2 here. So here, if the stage is reached here, when N2 is greater than N1 here, so this is the population inversion here. But it is very hard here. But this stage is achieved here by scientists here. So here, from that here, this equation we proved that here, at 10 raised to 4 degree Kelvin here, out of 10 raised to 6 here, only 6 to 7 atom goes to the higher energy here. So here, so this is nothing but the thermal equilibrium here, and we are familiar with that here. How it is possible to find out how it is possible, how it is very hard, very difficult to find out this situation here. It is population inversion here. Now then, another article is nothing but the metastable state here. Now what is metastable state here? Now we know that here. So here this is the ground state atom here, and this is the higher energy level here. It is your E1, it is your E2 here. It is your number of atom in the ground state here and number of atom in the higher energy level N1 and N2 here. As we know that here, if we supply some energy from the external source here, then the atom in the ground state goes to the higher energy level here. After 10 raised to minus 8 seconds here, what happens here? They return to the ground state at its own here. Now here, actually we require this population inversion condition here. What we require here? We require N2 should be greater than N1 here. So we require this condition here. So in this case here, in normal case here, it is not possible here. Atom goes to the higher energy level here, and after 10 to minus 6 here, minus 8 second here, they returns to the to the ground state at its pole here. So here we have to achieve the situation that here the N2 should be greater than N1 here. For that here we require one stage here. So here means what happens here, the population of the atom or lifetime of the atom in the higher energy level should be greater than the atom in the ground state energy level here. So here we have to create one stage here. So it is your E3 here. So here it is E3 is the metastable state here. It is in between ground state and higher energy level here. So here then what happens here? The atom, we know that here by supplying some energy from the external source here, atom in the ground state goes to the higher energy level here. Now here we know that here after 10 to minus second they return to the ground state at its own here, but they are restricted to go to the ground state here. They are restricted or they are restricted to go to the ground state here, and they are collected. So here, so these are atom here, these are the atom here goes to the higher energy level here, and they are collected at the stage here. So here they are collected in between this stage here, collected at the metastable state here. So it is your ground state, it is your higher energy level here, excited state here, and it is nothing but the metastable state here. So what happens here? The atom goes to the higher energy level here. Now here, we know here after 10 to minus 8 second they return to the ground state here, but they are restricted to go to the ground state here. And one stage is reached, it is created that here. In this stage is nothing but this state is nothing but the metastable state here. So here the atom which are in the higher energy level here, they are collected at the metastable state here. Then as compared to this E1, population of the atom in the ground state here and the population of atom in the high energy level here. So here by using this metastable state here, we achieve the population inversion condition here. So here the definition, what is the definition of the metastable state here? Metastable state is the state which is in between the ground state and higher energy level here, and the atoms which are in the higher energy level here, they are restricted to go to the ground state. They are collected at the state which is in between the ground state and the excited state here. This is the it is called the metastable state here. So here this is the metastable state here. So here thus here today we saw here what is thermal equilibrium here, what happens at 10 to what happens at normal room temperature here, what happens at 10 to 4 degree Kelvin here, and then this is how we this is the another article in the metastable state here. In the next lecture here we can see here what is the population, what is the pumping scheme here. So there are three types of pumping scheme here: 2-level optical pumping, 3-level optical pumping, and 4-level optical pumping here. Now here we have to see it in the next lecture here, but it is just it is a 2-level optical pumping here. It is 2-level optical pumping. So here it is 3-level optical pumping here. What is 2-level optical pumping here? So it is very simple that here just within 1 minute here, it is your E1 and E2. In detail we have to see in the next lecture here. It is E1 and E2 here. It is 2-level optical pumping here. There it is your 3-level optical pumping here. And what is 4-level? What is the pumping scheme here? That we have to see in the detail in the next lecture here. Till have a good day. Bye.